Hello everyone, in today's lecture we are going to study aromaticity of Benzenoid compounds, Azulenes, Metallocenes, Heterocycle, aromatic ions and Fullerene. So first start with Benzenoid compounds. Aromatic hydrocarbons containing benzene ring in their structure are termed as Benzenoid hydrocarbons. Benzene is a parent hydrocarbon of these compounds. We can study deeply by benzene ring. Here two structures of benzene representing they are calculus structures and are the resonating form where the number of or the position of pi bond is different in both of them. So this compound representing resonance hybrid of benzene ring. A more detailed study of the structure of benzene shows that each carbon atom is sp2 hybridized. It is bonded to 3 atoms using sp2 hybridized ion. Therefore, all of them are lie in the same plane. The example of benzenoid compound is naphthalene. In that, two benzene rings are connected or fused together two common carbon atoms. It is aromatic because its properties resembles those of benzene ring. Also 10 pi electrons were involved, 2, 4, 6, 8 and 10, right. 2, 4, 6 and 8 is equals to 10 pi electrons. Hence, it follows Huckel's rule of aromaticity, that is 10 minus 2 becomes equals to 8 divided by 4 equals to 2. Hence, n is equals to 2, this compound is aromatic in nature. Also they are having 3 resonating structures and this is a resonance hybrid of naphthalene. Also it is a cyclic planar conjugated system following Huckel rule of aromaticity. The naphthalenes, that is the benzenoid compounds, are aromatic in nature. Here are some examples of benzenoid compounds, okay, such as indene, naphthalene, biophenyl, anthracene, phenanthracene, etc. Then next point of this slide of this PPT is azulenes. Azulenes, this is the structure of azulene. They are generally present in these charged species, or this by having a charge they are present in this charged manner, where this cycloheptatriene is connected to cyclopentadiene. In the isolated form, both these structures are not aromatic due to not complete conjugation in both the rings. Require the tropylium ring, that is the cycloheptatriene, required a positive charge for complete conjugation, and number of pi electrons in cyclopentadiene are only 4. Also there is presence of one sp3 hybridized carbon which involves not complete conjugation. Hence, this cyclopentadienyl requires negative charge for become a aromatic species. In the fused carbon or in the fused cis, azulenes are having non-alternate 10 pi electron. Therefore, these are comes under non-benzenoid system due to presence of cycloheptatriene and cyclopentadiene. Here is not a benzene ring involved in the structure. These are the aromatic hydrocarbons which has a fused structure of 5 and 7 membered rings, although they are structural isomer of naphthalene, right, because they are also having 10 carbon atoms and 10 pi bonds. However, naphthalene is a colorless compound. Azulene shows a deep blue color. Therefore, its compound's name originates from the term azure or azul, which means blue in Arabic and Spanish respectively. Since the ionic cyclopentadienyl ion and tropylium ion structures contribute to the azulene skeleton, they give, that is the cyclopentadienyl ion gives electrophilic substitution reaction at 1 and 3 carbon atom, whereas it gives nucleophilic substitution reaction at 4, 6 and 8 carbon atoms. The reason for large dipole moment of 1.08 D and blue color of azulene despite the hydrocarbon structure is explained by intramolecular charge transfer derived from the polarized resonance structure. So, students, in this case we can see this compound, that is azulene, gives electrophilic substitution at first and third carbon atom. So, as it is a cyclopentadiene system, cyclopentadiene is stable by having a negative charge. In case of this azulene, it shows electrophilic substitution at first position. If we consider this carbon as a first carbon, then here is a generation of negative charge. So, generation of negative charge at this first carbon and generation of positive charge at the 9th carbon atom. Okay, that is negative charge at this carbon and positive charge at this carbon. Right. Okay. So, this charge separation will show that this is a cyclopentadienyl anion and this system is a cycloheptatrienyl cation, that is a tropylium ion. Hence, that becomes a aromatic in nature, right. Hence, these are stable, these are the aromatic hydrocarbons. However, there is a generation of charge. This charge development will lead to generation of dipole moment, which is not observed in aromatic compounds. However, this azulene system is stable by having a charge. Hence, due to this polarizability or this charge formation will rise to dipole, generation of dipole moment. Also, the blue color is due to this charge separation, having blue color due to this charge separation. In this system, we can find the system is aromatic or not aromatic by checking its or by passing C2 axis of symmetry. 2, 4, 3, 4, 5, 6, 7, 2, 4, 5, 6, 7. Okay. In this manner. Okay. So, if we pass C2 axis of symmetry by this molecule, if the number of carbon atoms remains same or if each carbon atom occupy position of another carbon atom after the rotation, then there is a presence of C2 axis of symmetry, and this may leads to explain that the compound is aromatic or not aromatic. So, let us pass C2 axis of symmetry by 2 carbon atoms or by whole the system. This is a carbon atom from which the axis, that is C2 axis, will pass. If we rotate this at 180 degree, it will show that this carbon will acquire position of this carbon will acquire position of this carbon, this will acquire this will acquire this. So, that there is all carbon atoms occupy position of other carbon atoms after the axis C2 axis or after the rotation, hence having C2 axis of symmetry. Therefore, the azulene systems are aromatic in nature. However, they are planar cyclic conjugated systems following Haeckel's rule of aromaticity. they are aromatic in nature. Another system we have to consider aromaticity of metallocenes. Here metallocenes are organometallic complexes with a central metal atom attached to aromatic ligand. Examples of metallocenes are most common is ferrocene, then nickelocene, cobaltocene, titanocenes, etc. Here is the structure of ferrocene and azulenecene. These are the metallocenes. We have already discussed that cyclopentadiene is aromatic when there is a generation of negative charge. As there is a generation of this ring current, it indicates that the CP rings are aromatic in nature, that is they are present in the form of cyclopentadienyl ion. Okay. Similarly, in case of azulenecene, the ferrocene can be generated by the treatment of 2-cyclopentadienyl anion along with the FeCl2 in THF. 2 CP rings, 2-cyclopentadienyl anion on treatment with FeCl2 may leads to generation of the sandwich structure, that is a ferrocene. Okay. The ferrocene is having two conformation, that are eclipse conformation and staggered conformation. We have already discussed them in the BSc level. The staggered conformation is present or available in solid state. This is a staggered conformation. Okay. Whereas the eclipsed conformation, in which 2 CP rings are parallel to each other, is present in gaseous state, available in gaseous state. The 2-cyclopentadienyl in ferrocene molecule obey Huckel's rule of aromaticity, that is 4n plus 2 pi electron rule. As we can see, they are planar, cyclic, completely conjugated system having n is equals to 1, hence these are aromatic compounds. Okay. Hence the ferrocenes are aromatic compounds. If we check the aromaticity of this cyclopentadienyl ring, that is the aromaticity of metallocenes or ferrocene, we can check, consider Friedel-Crafts acylation reaction. We have already discussed that Friedel-Crafts acylation of ferrocene will give us, in the first step, one acylated ferrocene, and in the second acylation will give us 2 acylated ferrocene, that is we are getting 1 dash acylated ferrocene. Also, if we carried out Friedel-Crafts alkylation of ferrocene, then in the first step alkylation of first cyclopentadienyl ring will carried out, and in the second or in the excess will get the product, major product, in which another alkylating group will connected to the same cyclopentadienyl ring. Here the difference in this substitution product is just because the acetyl group in case of acetyl chloride is highly electron withdrawing in nature due to polarizability, right. When this acetyl group connected to one CP ring, as its electron withdrawing nature, this CP this acetyl group due to its electron withdrawing nature pulls electrons of this CP ring towards itself, making this ring electrophilic in nature, that is pi electrons are less available after the substitution of this acetyl group. Hence, pi electrons are available in this second CP ring. Therefore, electrophilic substitution of acetyl group will occur in the second ring, Therefore, here we are getting 1 dash acylated ferrocene as a major product, whereas in case of alkylation of ferrocene, the alkyl groups are electron donating in nature. When the first introduction or first substitution of alkyl at the CP ring will occur, that may provide its electrons to this CP ring, making it more electron donating or electron rich species. So, the second nucleophilic electrophilic attack will occur on the same CP ring. Hence, we are getting 1,2 disubstituted ferrocene molecule. Now, let us proceed towards another species, that is aromaticity of heterocycles. As we have already discussed the compounds pyridine, pyrrole, furan, thiophene, they are already available in the aromatic compounds, and we are going to study its aromaticity. When the number of carbon atoms in the benzene ring or any other aromatic compounds are replaced by other other atoms other than carbon atoms, such as heteroatoms, such as for example oxygen, nitrogen, sulfur, then they are termed as heterocyclic compounds. In that, first we will discuss about pyridine. Pyridine have, in that structure we can see pyridine structure is similar to benzene ring structure, where the one of the carbon atom is replaced by nitrogen atom. Hence, it may leads to generation of pyridine. That pyridine is aromatic in nature because all the carbon atoms along with the nitrogen are sp2 hybridized. In this case, p orbital of nitrogen is involved in the delocalization with p orbitals of carbon of the ring, whereas this lone pair is not involved in the delocalization due to its perpendicular overlap. Also, there are 6 pi electrons. The compound is cyclic, planar, completely conjugated. Following Haeckel's rule of aromaticity, pyridine is aromatic in nature. Now, if we compare pyridine along with this pyrrole, the pyrrole, in case of pyrrole, the pi lone pair of this nitrogen is not available on the nitrogen. It is involved in the delocalization, as in the cyclopentadiene, one carbon atom is replaced by NH unit, in which nitrogen having lone pair of electron, it is sp3 hybridized, but due to this nitrogen is connected to sp2 hybridized carbon atom, its lone pair is not available on the nitrogen. It is involved in the delocalization. Hence, it is considered to be sp2 hybridized nitrogen. Also, due to the introduction or involvement of this lone pair of electron on the nitrogen, the number of pi electrons becomes 6. The system is cyclic, planar, conjugated, and following Haeckel rule of aromaticity, the pyrrole is aromatic in nature. Similar to pyrrole, furan and thiophene also having lone pair of electrons, they are involved in the delocalization. Hence, they all becomes also aromatic in nature. If we check nucleophilicity of, or if we compare nucleophilicity of pyridine and pyrrole, or basicity of pyridine and pyrrole, then pyridine is more basic as compared to pyrrole, because in case of pyridine, lone pair of nitrogen is available for donation, whereas in case of pyrrole, lone pair is not available for donation. It is involved in the aromaticity, therefore, it is never ever gives its lone pair to become anti-aromatic compound. Also, if we check the stability or the aromaticity of pyrrole, furan and thiophene, or the electron donating nature of pyrrole, furan and thiophene, the thiophene having highest priority than pyrrole, whereas pyrrole having highest priority or highest aromaticity as compared to furan. Now, oxygen and sulfur are comes from one family, that its only one lone pair is involved in the conjugation to become a aromatic compound, whereas another lone pair is available for donation. However, in case of pyrrole, there is only one lone pair of electron and that is involved in the delocalization. It is more stable or more aromatic as compared to this furan, or more basic as compared to this furan. The reason behind that is the sulfur is less electronegative than nitrogen and oxygen, hence it can easily share its lone pair of electron. However, this pyrrole is less electronegative than this oxygen atom. The more electronegative oxygen will not easily share its electrons, lone pair of electrons, hence it is less basic as compared to pyrrole and thiophene. These are the resonating structures of pyrrole, and this is the resonance hybrid of pyrrole. Then let us proceed towards another slide, which is aromatic ions. We have already discussed cyclopentadienyl anion, then cycloheptatriene cation in today's lecture. Along with, we have already studied this cyclopropynyl cation. All this system we have already discussed in the previous lectures. All of them are stable due to the formation of charge on them. In case of cyclopropynyl cation, if the neutral system, that is cyclopropene is there is no complete delocalization, also not planarity, due to the presence of this sp3 hybrid carbon atom. If we remove one of the proton in the form of hydride ion, that is removal of H minus ion, will leads to generation of positive charge on this cyclopropene ring, and then the number of pi bond in this system is only one, which is odd, and generation of positive charge will involve complete conjugation, and that may leads to planarity to the system. Hence, following Haeckel's rule of aromaticity, this is aromatic ion. Due to generation of positive charge, the system becomes aromatic, hence it is comes under aromatic ions. In that same manner, cyclopentadiene, after the removal of H plus ion, it may leads to generation of negative charge on the system. Hence, the number of pi electrons becomes equals to 6, and 6 is a Haeckel number. Therefore, after the removal of H plus ion, cyclopentadiene becomes aromatic in nature. Similarly, cycloheptatriene having one sp3 hybridized carbon atom, which after the removal of H minus ion may undergo formation of positive charge on the system, that can be convert the carbon from sp3 into sp2 hybridized. Then it is possible to complete conjugation of the cycloheptatriene system, that is complete conjugation of pi bond to stabilize the positive charge on the system. Number of pi bonds becomes equals to 3, which is odd, and hence the compound becomes aromatic in nature. Then the last part of today's lecture of this video is Fullerene system, that is C60. It is a allotrope of carbon, that is the third allotrope of carbon. However, two allotropes are diamond and graphite. Fullerenes are closed hollow cages consisting of carbon atoms interconnected in pentagonal and hexagonal rings. We can see that here is a hexagonal ring connected to a pentagonal ring. A fullerene is a pure carbon molecule having C20 being the smallest one. C20 is also a fullerene which is a smallest one. The well known or the famous fullerene is C60, which is also known as buckyball. Fullerenes have extensively used in biomedical field for the application of designing of high performance MRI contrasting agents, X-ray imaging contrasting agents and photodynamic therapy and drug and gene delivery. Here it is the brief history of fullerene. The C60 was named by Buckminster Fullerene in the honor of Buckminster Fuller. The shortened name fullerene is used to refer to the family of fullerene. Robert F. Cort, Sir Harold W. Coroto and their colleague Richard E. Smalley were together are the inventors of the fullerene, or they have get Nobel Prize in the chemistry for their discovery in the fullerene. Here is the structure and bonding of C60. C60 contains 12 pentagons and which are surrounded by 20 hexagons. Each carbon atom is a part of one pentagon and two hexagons. Each has two single bonds and one double bond for traditional carbon valence of 4. The fullerene hybridization is not fixed, but the variable characteristics depending on number of carbon atoms in the molecule. Just a minute. The fullerene is spherical. Fullerene shows spherical aromaticity, and the criteria for spherical aromaticity is 2 into n plus 1 bracket square number of pi electron. This rule was invented by Hirsch, Hirschs, and it is termed as Hirsch rule. This rule is applicable for the compounds up to 50 pi electrons only. This fullerenes never ever shows electrophilic substitution reaction. This is because of the formula or general formula of fullerene, that is Cn. There are only carbon atoms, presence of only carbon atoms, which never ever gives replacement of hydrogen by any other electrophile. So that fullerene system never shows electrophilic substitution reaction. They only gives addition reactions. Okay. In fullerene, 6-membered rings are aromatic in nature and 5-membered rings are anti-aromatic in nature. Therefore, it is difficult to explain aromaticity of fullerenes. So, by using this rule, let us study are the fullerenes are aromatic or not aromatic in nature. The rule is 2 into n plus 1 bracket square number of pi electrons. Okay. Let us consider first C60. It is anti-aromatic in nature. Why? Because this rule is applicable for only 50 pi electrons, and in the C60 there are 60 pi electrons are involved, right. If we compare C60 plus 10 that is carbon having plus 10 oxidation state. Therefore, 60 electron minus 10 becomes equals to 50. Hence, the compound becomes aromatic in nature. Then we can take another example, that is of C20. It is also anti-aromatic in nature. The reason behind that is 20 divided by 2 becomes equals to 10, which is not a square of any other number. Therefore, it is not following Hertz's rule, hence it is anti-aromatic in nature. If we compare C20 plus 2 system, then 20 minus 2 is equals to 18 divided by 2 is equals to 20 minus 2, that is carbon having oxidation state of plus 2, that is the number of pi electrons become equal to 18. We have to divide this number by 2, hence the number becomes 9, and 9 is a square of 3, right. We have to convert this form into n plus 1 format. Hence, 3 is equals to 2 plus 1 square. 3 square of 3 becomes equals to 9 into 2 becomes equals to 18. Hence, C20 plus 2 is aromatic in nature. So, by this way we have covered all these things. Hence, thank you.